So in week 3 ECG 575, we are still in this topic, chapter 1, 2D flow in soil. So for this slide, the learning outcome is to determine the pore water distribution along the base of the dam and also along the front face and back of the sheet pile. And then we will calculate the uplift force using the Simpson's rule. We need to determine the maximum hydraulic gradient, and at the end we will evaluate the occurrence of piping. Okay, now we start with the pore water pressure distributions. Last week, the lecture focused on the pore water pressure at any point within the flow net underneath the concrete dam. So for this week, we will discover the pore water distributions along under the base of the dam. I'm still referring to the exercise 1, okay, but with the presence of the sheet pile here on the left side of the concrete dam. So if you can see here, the red line, okay, along the base of the dam. So this is our focus to check or to determine the distributions of the pore water pressure, okay, from point A to the end of the concrete dam. Okay, so from this exercise, I have the NF equal to 3 and ND, the equipotential number is 18. So already set the datum at the lower part of the soil layer. This is the datum. So we have the upstream level 12 meters and the soil layer is 13 meter. So now what is the step? So the first step, we need to divide the base length of the dam into a convenient numbers of interval. So use an even number of intervals, for example 6, 8, 10, not the odd numbers like 5, 7 and 9, because later in the calculations of uplift force, okay, we will use Simpsons that need these intervals. Okay, alright, so that's why in this example the length of the base is 25, so I divided by 10. So we have that each interval will have the distance or the delta x is 2.5 meter. And then the delta H head loss, okay, as I hope you still remember that last week we have the head loss for each equipotential line is H divided by ND. Okay, the H is 12 minus 1 meter here. Alright, so we have 1 meter here. So we have 1 meter here. So 12 minus 1 is equivalent to 11, and ND is the number of equipotential line, which is 18. So we have the delta H loss for each equipotential line is 0.611 meter. Okay, then what we need to do is to mark each point that measure 2.5 from each point. Okay, so now since the delta x for each interval is 2.5, so we measured 2.5. So I start from the left side of the concrete dam, so I label as a point A. So from point A measured 2.5 meter and the label as B, another 2.5 level as C, another 2.5 level as D. Still the point at the end of the dam, which is point K, also each of the interval have 2.5 meter distance. Okay, now after that we need to identify the ND drops for each points, meaning that we need to know the numbers of equipotential line at each point. For example, for point A, so for point A, since I start the base of the dam is from point A, so this is x point equal to 0, and the ND is 7.4. How I get the 7.4? Okay, so I consider the flow nets on the right side of the dam. If you can see that at the left side, for example, ND number 1, number 2, number 3, 4, 5, it is actually due to the sheet pile. Okay, it is due to the sheet pile. So if you look at point A, B and C, D and so on till point K, it's more on the flow line at the right side. So that's why I use that 7 point something for the ND at point A. Okay, so at point A, okay, roughly estimate, because the flow line, the equipotential line is between 7 and 8. So within the 7 and 8, we can also have another flow equipotential lines in the point form of number. For example, if we have 7 and equipotential line 8, so in order to get point A, so we project the line and roughly estimate that at point A the ND is around 7.4. okay, and we look at another example at point B, still in between 7 and 8. So we project the line and estimate that point B is around 7.6. okay, and point C again within 7 and 8, since it's close to line ND equal to 8, so we roughly estimate that at point C the ND is 7.98. and we look at another example at point F. So at point F, the ND is in between 10 and 11. It looks like in the middle, so that's why we roughly estimate that the ND value is 10.5. So this is how we identify the ND drop for each point from A to K. Okay, I hope you understand this part. Alright, now what we need to do is to tabulate the calculations of the pore water pressure at the base, so it's more easier to analyze the data. So since X, the delta X, the difference between each point is 2.5. okay, this is plus 2.5, this is plus 2.5 till you reach 25. And the ND as at previous slide, and the head loss for each point, just using this equation, we have the delta H that we measured earlier, okay, 0.611. alright, so times with each ND, so we will have this head loss. And we also need to calculate the total head. Actually, the equation, the step is similar with how we determine the pore water pressure at any point within the flow net. Okay, the step is still the same. Okay, but this is, for this exercise, we have more than one points along the base of the dam. So HT, we have the head upstream at the upper stream, 12 plus 13, which is 25, and minus with the head loss at this column. Okay, so we will have 20.478 for example for this one. And then the elevation, so the elevation is from the datum. Okay, so we have the datum here, so the point is located here along the base. By knowing this is 13, this is 1.5, so we know that the distance between A to datum is 11.5, which is 13 minus 1.5. okay, alright, so since all the point is located at the same point from the base, so the HE is 11.5 for all the points. And then we need to calculate the head pressure. So head pressure is H total minus HE, so we will have this value. And then to get the pore water pressure, we need to time the head pressure with the unit weight of water, 9.81. so this is the value for the U. Okay, now what we need to do is to plot. We need to plot the distribution of pore water pressure on the graph. So the y-axis is the U value, and the x-axis is the length of the base. Okay, 0 to 25. Okay, so this is the distributions of the pore water pressure along the base of the dam.